presentations. Our first speaker is Peter Schulem. He's going to be talking about what-if reasoning using counterfactual Gaussian processes.
All right. Good afternoon, everyone. I'm Peter Schulem. I'm from Johns Hopkins University, and this is joint work with my advisor, Professor Suchi Saria. So this talk is all about leveraging data to help people make safer and more reliable decisions. And to better understand the problem, I want to start with a really simple sort of data analysis narrative. Let's say our job is to determine whether this particular patient is at risk of dying, and we want to use all these medical test results that we have available. So things like their temperature, blood pressure, heart rate. And we've got two data sets. Each is collected from a different hospital, and our plan is to use them to train a model that will predict death given these medical test results. We train a model on each each data set, but something strange happens. One says that the patient is at high risk of dying, and the other one says that this very same patient is at low risk. So let's try to debug this a little bit. The hospitals serve nearly the same exact patient population, so this isn't the cause of the discrepancy. The data sets are also large, so the difference isn't due to sampling variability. And we've carefully selected these features. So these are test results that should give us a really good picture, or at least a reasonable picture, of this patient's health. So what's the issue? We find out that the two hospitals have very different treatment guidelines. Hospital A uses high temperature as a criterion for very aggressively treating the patients. So the learner, when it uses data from Hospital A, is seeing far fewer examples of patients with high temperature that then died. And so it will predict low risk for people with this feature. Now, on the other hand, doctors at Hospital B don't use high temperature as a criteria. And so when we train a model on that data, we're going to see, or the model will make predictions, the model will predict that the people with high temperature are at high risk. So what's happening is that the models are making different predictions because of a phenomenon that I'm going to sort of informally call for this talk policy creep. And so what's happening is when we used a supervised learning objective, our models captured policy-dependent relationships in the data. And these relationships don't generalize when the policy changes. So now why is policy creep a problem? To start from a doctor's perspective, it might be extremely unsettling that these so-called objective decision support tools are drawing drastically different conclusions for the same exact patient. But more importantly, it's super unsafe. So if we had deployed the model that we learned from Hospital A, we could actually cause doctors or lead doctors to undertreat people who are at risk because of their high temperature, which would increase their chance of dying. Now, you might be asking, how prevalent is this problem? And this issue isn't specific to medicine. In fact, we need to be careful whenever there's a shift in the policy choosing actions between our train and test environments. So for example, if you were to deploy a generic model to help people choose their decisions, as soon as people start using the model, they're actually choosing their actions using a different policy. So the training data policy is now becoming something different that depends on the model's predictions, and we're going to experience this policy creep. So to summarize, in order to build reliable decision support tools, we need to learn in a way that is stable to changes in these policies. Okay, so I'm going to tell you about one possible alternative learning objective that will generate models that's less susceptible to this policy creep problem. To explain it, I want to use a really simple thought experiment. For any patient, suppose we could split into two realities. And in one, I'm going to give this patient a blue drug, and in the other, I'm going to give them some green drug. If we could see the two outcomes, so for example, whether or not the patient died when I gave them one drug or the other, and we'll call these outcomes counterfactuals. If I could see them before making my decision, then I could compare the two outcomes, and I could choose the treatment that leads to the best result. Now, of course, I can't actually split reality, of course, but in some cases we can still learn to predict these potential outcomes using data. So what we're going to do is show how to learn counterfactual models in the following general sequential decision-making setting. So here our outcome is a function of time. And there's a decision maker who chooses to measure or observe the trajectory at arbitrary times. The same decision maker is also trying to influence the trajectory by taking actions, also at arbitrary times. So as a point of comparison, if you're familiar with a Markov decision process, there we assume that outcomes are observed and actions are taken in lockstep in discrete time, which is something we don't require here. To build reliable models in this setting, we're going to develop the counterfactual Gaussian process, which allows a decision maker to predict and compare the full distribution over outcome trajectories under various hypothetical action sequences. So as an example, we could ask the counterfactual GP, what's going to happen if I don't take any more actions after this point? Or what would happen if I gave this person one more dose of the green drug, or maybe 2 doses of the blue drug? So we're going to show how to learn the counterfactual GP from easily accessible retrospective data. Now, the key challenge when learning counterfactual models from retrospective data is the presence of confounders. So informally, confounders are variables that the decision maker uses in the training data to choose their actions and that are also predictive of the outcomes by themselves. They're a problem because they lead our models to learn a relationship between actions and outcomes that depends on the policy and that doesn't generalize when the policy changes. When there are confounders in the data, it's still sometimes possible to adjust for them under certain assumptions and learn counterfactual models. So to learn the counterfactual GP, we're going to use observational traces, which are these sparse, irregular sequences of outcomes and actions. And critically, we're not going to assume that we know the policy that was used to generate these actions. And there are a couple of types of confounding in these observational traces that make learning the counterfactual GP challenging. One is that the timing of measurements and actions are choices made by the decision maker and so can be confounded. This is something that we don't need to worry about, for example, in discrete time settings. Another type of confounding is due to the fact that the decision maker chooses actions dynamically based on the effects of past actions, which creates a feedback loop between actions and outcomes. One simple example is adjusting treatments. If a doctor prescribes a drug and it doesn't seem to be working based on their past actions, they might try a different one. But here's a more subtle example. If a doctor is measuring lung capacity and notices a downward trend, they'll order the next measurement sooner than usual, and they may continue to do so as long as the patient looks like they're deteriorating. In other words, observations and the choice of actions have this feedback loop that happens repeatedly over time. Now, when we want to learn counterfactual models under a sequence of these dynamically chosen actions, we need to perform a sequential adjustment procedure. So to learn the counterfactual GP, we build a joint model using a marked point process. Essentially, this combines a point process model of when events happen with a Gaussian process that models the outcomes of our trajectory given the past actions. Under certain assumptions, which I'm not going to describe in detail here because of time constraints, but we rigorously develop them in the paper, we can fit the marked point process using maximum likelihood and recover the counterfactual GP. And this is awesome because now we can use the CGP to predict counterfactual outcomes under hypothetical action sequences that we would otherwise have no way of observing and comparing. Importantly, these counterfactual predictions are also stable to changes in the action policy. So now let's show that the CGP is indeed stable. We designed a simulation where we create a single test set in 3 different training sets. The only difference between these training sets is the policy that was used to choose the actions. Our goal is to learn models that predict the patient's risk so we can decide whether or not we should treat them. To assess the risk, we're going to use the counterfactual GP to predict the outcome under a policy where we give no further treatment. And as a baseline, we're going to compare it to a classical conditional model that looks at the future outcome given the history we've seen so far. So first we compare how the 2 models' risk predictions change on 2 data sets where we've designed the policy so that they satisfy the assumptions we need to learn the counterfactual GP. What we see is that the CGP's risk scores are stable, but that the baseline GP's predictions change when the policy does. But more importantly, these instabilities have a measurable impact on downstream decisions. For example, if we triaged by using risk scores to order patients by severity, the baseline GP ranks the same patients differently depending on the training policy, but the CGP is stable. Now, to frame these numerical results, the experiments confirm that the risk assessment made by a classical predictive model heavily depends on why the treatments were given in the training data. The CGP, however, is stable with respect to these shifts in policy. Now, to show you why these assumptions about the confounders are important, we also compare the baseline and CGP on a third data set, where the policy is designed to violate our assumptions. And in this case, both models are unstable. Now, finally, as a brief teaser, our paper also includes a qualitative demonstration of early work where we've trained the CGP on real hospital data and showed how it can help support decisions about who should and shouldn't be on dialysis, which is an expensive therapy needed by patients with failing kidneys. Okay, so to wrap up, at a high level, we've shown that we need to think very carefully about subtle sources of bias when we're deploying machine learning in high-stakes applications. Our work addressed one particular type of bias, which we called policy creep, that can occur when we learn models for decision support. To address the bias, we proposed using counterfactual models, which allow us to make reliable predictions under policies that weren't used to generate the training data. And we developed a particular model, the counterfactual GP, to support decisions in a general sequential decision-making setting where we can't assume discrete time actions and outcomes. Now, we showed, however, that the benefits of counterfactual models critically depend on the assumptions about confounders, and this suggests interesting follow-up work to understand how we can systematically stress test these models to understand how they might fail if the assumptions are violated. And finally, I want to point out that counterfactual reasoning is complementary to other efforts in our community to increase the reliability of our models by making them more transparent. Counterfactual reasoning guides our choice of what we should learn from the data, but we can still make choices about how to parameterize our models to increase the transparency and interpretability of the results, and I think this is a very fruitful direction for future work. So thanks very much, and I'll take any questions in the remaining time.
For questions, please go up to the microphones. So let's say you have a patient and they may have a BMI that has a different response to a particular dosage of a drug than the rest of the patients in the database for pediatric patients, for example.
Yeah.
How do you control for something like that, whether it's latent or observed?
So if it's observed, it's something we'd want to contain in the conditional model. And it's no problem if it's not observed as long as it's not a confounder. If it's not observed, what's going to happen is we're going to get an effect distribution that has a wider skew or a wider more uncertainty, basically, just because we're accounting for that unobserved thing that's mediating the treatments or controlling what our effects are.
It's been great work, and I really enjoyed the stability analysis. I think that's a really great contribution to the community.
Thanks, David.
Could you talk a bit about how you parameterize the treatment effect and whether you had to do whether there were any changes you had to make to the learning algorithm to guide the learning algorithm to pick up that you want the treatment to do something, whereas often what you find is the covariates are so informative about where the patient is going to go next that your learning algorithm might actually ignore the treatment.
So I think you're asking, so basically, how do we look at the form of what the treatment's going to do to the future outcome trajectory? Is that what you were asking?
And how you might regularize that or otherwise change that, or how the choice of architecture there actually affects your results.
Yeah, so it turns out that this is actually very important, and the reason why is because GPs are flexible enough to essentially, well, if we don't regularize the hyperparameters of the GP enough, they're going to pick up some of the effects that we think might be picked up by the treatments. So in our case, when we, for example, looked at dialysis, we used a set of differential equations to define a parametric form for what looks sort of like a dose-response curve. And that was basically because we know how dialysis works. But in a more general setting, so we haven't thought much about how you'd sort of discover in a totally flexible way how the effects might look. But it does require some generalization or some regularization.
Great, let's thank Peter.
Thank you again, everyone.
Next up, Mark Vanderwilk is going to be talking about convolutional Gaussian processes.
All right. Hi, everyone. My name is Mark van der Wilk, and I'm very pleased to talk today about our work on convolutional Gaussian processes. So this work was done together with my supervisor, Carl Rasmussen, and James Hensman, also at the Prowler. So before getting stuck into convolutional Gaussian processes immediately, I just wanted to take a minute to kind of recap why I think it's important to study Gaussian processes. So I think there's one crucial property that Gaussian processes have, which I think makes it really interesting, and that's the fact that a Gaussian process can be seen as a Bayesian neural network with an infinite number of basis functions. And I think that this property of having a large number of basis functions combined with doing Bayesian inference is crucial for the Gaussian process's ability to be able to capture uncertainty well, particularly far away from the training data. So to illustrate this is a toy example. We see here a finite basis function model with the prior and the posterior, and we see that the certainty that the model has far away from the data is far too much. A Gaussian process, on the other hand, has an infinite number of basis functions and distributes them uniformly over the space, and therefore can represent uncertainty even where it hasn't seen any data. So essentially, our convolutional Gaussian process can be kind of seen in the same way, in the sense that it can be seen as a Bayesian convolutional neural network with an infinite number of filters. So with that out of the way, I wanted to jump straight into constructing the convolutional Gaussian process. So the task we're trying to solve is to create a Gaussian process on f, which is a function from images to real-valued responses, and we want it to have convolutional structure. Our images are of size capital W by capital H, and we can divide the image input into capital P patches of small w by small h. These patches can overlap just like in neural networks. So to illustrate, MNIST would have 576 different patches. We construct our patch response function our image response function f by starting with a patch response function. This is similar in spirit to how convolutional neural networks work, since convolutional neural networks take the same multiple linear features which they apply to different patches in the image. We apply our nonlinear single patch response function to all the patches. This results in a convolved image, which we then pool by summation in order to get our image response. This straight summation is quite restrictive in the sense that it imposes a kind of translation invariance, so we can also remove this translation invariance by doing a weighted summation of the patch responses. Now, you can note here that the operations that we perform on G, the patch response function, are all linear in order to get f. So if you place a Gaussian process on the patch response function G, this actually implies a Gaussian process on f as well. And we can find its kernel by considering the covariance between the Gaussian process at two different image input locations. This covariance ends up requiring the sum over every pair of patches in the two input images that we're trying to consider. So given this definition of the kernel, we already have enough to perform exact Gaussian process inference if we have a model with a Gaussian likelihood. However, this procedure has two well-known problems in the sense that it scales very badly with the size of the data set. So Gaussian processes need to invert a large matrix, which requires a cubic amount of computation. And secondly, exact inference is intractable in the case of using non-Gaussian likelihoods. In our case, we're specifically interested in classification problems, so we're going to need approximate inference. Luckily, there's a single framework to solve both these problems, which is the variational inference framework. So this framework has been developed over a long period of time, and the final contributions that kind of led up to enabling this work were the removal of the large matrix operation, the large inverse, the development of mini-batching schemes in the variational lower bound, and the ability to incorporate non-conjugate likelihoods. All these contributions led to the variational lower bound that you see below, and this is the variational lower bound that we're going to use. So the nice thing about this variational lower bound is that if you optimize it, you actually minimize a KL divergence between an approximate tractable distribution over functions to the true posterior distribution over functions given your data. Now, given that we have a variational lower bound, we also need to define a class of tractable approximate distributions that we're going to that we're going to find our solution from. And in the Gaussian process inference case, the class of tractable distributions is essentially the prior conditioned on a small number of points. These points are called inducing points, and essentially determine the shape of the posterior. So in the toy example below, we have a dense problem on the left and an approximate posterior on the right, and we can modify the shape of this approximate posterior by changing the location of the inputs and the outputs of those inducing points. So the inducing inputs and the inducing outputs essentially become variational parameters. And it's the goal of the variational inference algorithm, so by optimizing the lower bound, we want to choose these inducing inputs and outputs such that the posterior that we parameterize is close to the true posterior. Now, there's one nice thing to note here, and that's that the error bars from the infinite number of basis functions that the original model have are actually maintained in the approximation. The posterior is also tractable, as you can see in the equation below. It requires only an inverse of this KZZ matrix, which is the covariance of every single pair of inducing points. We use Z to indicate the locations of the inducing inputs. Right, now, so to what extent does this standard approximation technique help us with performing inference in convolutional Gaussian processes? Well, it solves two problems. It solves the problem of dealing with the approximate likelihood, with the non-Gaussian likelihood, and it solves the problem of having to invert this large matrix. However, we still need to evaluate covariances between the inducing points and our observations. And as we saw earlier, this requires p-squared evaluations of the patch covariance. So, as an illustration, if we take MNIST with 5 by 5 patches, we would require 330,000 kernel evaluations per pair of images that we want to find the covariance of. So, even if we applied sparse variational inference for the Gaussian processes, our inducing point matrix, which is supposed to be tractable, would require 700 gigabytes of memory, which is totally infeasible. So this illustrates the fact that the convolutional Gaussian process is actually intractable in a different way to general Gaussian processes. Now, the solution essentially comes from interdomain Gaussian. Is inspired by interdomain Gaussian process approximations. And the idea behind interdomain Gaussian process approximations is that instead of learning about the function that you're interested in directly, you learn about a function which is linearly and deterministically related to the function you're interested in. Now, interestingly, this mirrors really nicely how we constructed our convolutional Gaussian process. Since our patch response function, G, is linearly and deterministically related with our function on images, F. So here I show a toy example of a convolutional Gaussian process on 2 pixel images. So on the left we have the variance of our function f, and we have on the horizontal and vertical axis the 2 pixel intensities. And on the right we have g, our patch response function. And we see that as we add more inducing points, we constrain the variance on f, and we also place constraints on g. Now the thing that makes convolutional Gaussian processes work is by placing the inducing points in the space of G instead of F. If we do this, we can still constrain the function we're interested in the same way, only we only have to care about covariances in G and between G and F, which don't require these intractable double sums. The covariances between inducing points themselves require no sums at all, and the covariances between inducing points and observations require only a single sum. So to round up, I just wanted to summarize some results. So we compare to an RBF Gaussian process, which obtains about 1.9% error on MNIST. Our translation invariant convolutional Gaussian process performs worse, so the translational invariance is too strong. But the weighted convolutional Gaussian process, where we remove this translation invariance, performs better. We also show in the paper that the convolutional Gaussian process, or the convolutional kernel, is not universal, so it loses the universal approximation property, which can be remedied by adding a small RBF component which can mop up any residuals. We also apply our method to CFAR10, and we show a significant reduction in error compared to the RBF. Now, we acknowledge that these results aren't competitive with deep neural networks, and this may not be surprising since a Gaussian process is a single-layer model. However, we hope that this convolutional Gaussian process can be a building block on which more complicated Gaussian process models can be built. So to wrap up, we create a convolutional Gaussian process, and we introduce practical inference, which is tailored to the structure of the model. And we do this within the variational approximation framework, which maintains some of the nice non-parametric properties of the original model. So the code is available online. It's based on GPFlow, which is essentially a software package where we're trying to make Gaussian processes as easy to use as deep learning. I hope we're making some progress. And otherwise, thanks for your attention. And if you're interested in more, come see us in poster 196.
Questions for Mark? We have a few seconds.
Hi, nice talk. I was wondering if you compare to a single layer CNN?
We haven't done that experiment directly, but that would be interesting to do, yeah.
Okay. And then how you would envision to add layers?
Sorry?
How would you envision to add layers?
Well, there's another spotlight talk later on which talks about deep Gaussian processes, and I think the two can be married quite easily.
Thank you.
Thanks very much.
Let's thank Mark again. Okay, our next speaker is Matt Kushner talking about counterfactual fairness.
Great. Hello, everyone. I'm Matt Kushner. And this is joint work with Josh Loftus, Chris Russell, and Ricardo Silva. I want to start off this talk by saying, congratulations. We did it, fam. To everyone here. Machine learning is making life-changing decisions, everywhere from predictive policing to who to give loans to. But we have significant problems. For example, the face detection system that can't see the faces of black people but sees the faces of white people perfectly okay. From natural language processing systems that associate men with president or leader and women with helper assistant, these sexist associations. In this talk, we provide a solution. We give an intuitive definition of fairness that states a fair classifier gives the same prediction had the person had a different race or sex. We give two contributions, a metric to test whether an algorithm is fair based on this definition, and an algorithm to learn fair classifiers. Let me illustrate this by giving an example of law school admissions. Imagine we're a law school, and we'd like to be able to predict law school success in order to figure out who should be admitted. We have this information about individuals, their sex, their race, their undergraduate GPA, their LSAT score, the law school entrance exam, and finally, their first-year law grade, which many law firms are going to use as a proxy of someone's law school success or potential. And so, as a law school, we're going to try to learn a predictor, y hat, that maps these features to predicting law grade, or label y. Now, right off the bat, people are going to be hesitant to use features like sex and race. Because if we do, we're explicitly discriminating based on these features. People who have different values of these features are getting different predictions. So what we're going to do is we're going to say these features are, in some sense, sensitive attributes, A. Now, because of this sensitivity, one sort of natural thing to try is to do a method that's called fairness through unawareness, in which we simply just remove these features from our prediction and just make a classification based on the remaining features. But there are crucial problems with this. While we suspect that undergraduate GPA is influenced by how knowledgeable you are, there's also evidence that's also unfairly influenced by sensitive things like race. The reasons are that minority students may feel that certain teachers are unsupportive, which may affect their performance. And by the same token, teachers may believe that minority students have behavior issues which causes them to treat them differently. The same goes for the LSAT score. This could be due to class placement or due to an economic history that is specifically based on race. So what we're trying to do, remove the sensitive attributes, we didn't succeed because the features themselves are biased. So we might take a different approach. In a recent work out of last year's NIPS called Equality of Opportunity by Hart et al., they propose a different fairness mechanism. They say, okay, why don't we construct a predictor based on features and sensitive variables? But crucially, we're going to make sure that for this predictor, we're equally accurate for different races. In particular, equally accurate for predicting law school success. But what if race also influences law school success? And there's evidence that it does. Because of the biases I just told you about, there's fewer minority teachers in law school, and because of this, it affects minority students' grades and their law school outcomes. So this may result in something like 35% of black students being successful at law school and 50% due to this unfairness of white students being successful. So it doesn't account for the fact that the label itself may be biased in this case. We take a different approach. We propose to model these unfair influences using causal models. Let's represent each of our features and label by some variable and represent this influence of race as a causal influence. Similarly, we may suspect that sex also influences each of these features and label. Finally, we may also suspect there's this unobserved quantity, someone's law knowledge, that influences these variables. And the beautiful thing about having a causal model is it allows us to model how the unfairness occurs in this problem. How does it work? Well, every arrow in this causal model specifies a functional relationship between the two variables that it's connecting. For instance, the arrow from variable u to y says that y is a function of u, and maybe a deterministic or a non-deterministic function. So how does this help us? Well, let's go back to our goals. We said we wanted to be able to test for algorithms that are fair with respect to this definition using some metric, and then design an algorithm to learn fair classifiers. Well, it turns out counterfactuals allow us to do this perfectly. So let me show you how. By starting off with imagining that we have a classifier that just uses college GPA and LSAT score to predict law school success. Further, let's imagine that we have this individual with these sort of features. We can compute with counterfactuals the answer to the following question. What if this person had a different race? How would that have affected their features and their label? We can do this using a simple three-step procedure. The first step says, let's compute all unobserved variables in our causal model. So this is our causal model. It's simply just the u variable that we haven't observed. And so this is what it might look like. The second step of this algorithm is to make the counterfactual change, the change in race. So let's imagine this person, instead of being black, had been white. In the third step, we're just going to use the model equations in the causal model, the counterfactually changed variable, and the unobserved variable to recompute g, l, and y. I'll denote these variables, these counterfactual variables, in this way, and these are what we might get. So, what this means is a classifier is fair if it gives the same predictions on the original data that it would give on the counterfactual data. More generally, any predictor y hat is counterfactually fair if given features x, sets of variable a, it ensures that the distribution of predictions for any counterfactual quantity are identical. Now, I'd like to contrast this with some very recent work, actually at this year's NIPS, by Kilbertus et al. And what the difference is they use the do operator instead of counterfactuals. What this means is that while our definition compares the same individual with a different version of him or herself, their definition compares different individuals that happen to align on the observed features. So it's a sort of a group level definition. Now, usually, classifiers aren't going to be counterfactually fair. So how do we construct these predictors? Well, the crucial thing to notice is that anything that's downstream, that's a descendant of our sensitive variables, is going to be affected or polluted by the effects of race or sex. So these variables, if we use them, we can't construct a counterfactually fair predictor. However, anything that isn't downstream, any features that aren't descendants, we can use, and we can guarantee that this is a counterfactually fair predictor. So how do we actually learn this predictor? I'll give you an algorithm. Given a set of features, a label, and a set of sensitive variables, we use the 4 following steps. First, fit the causal model you believe best represents your data. Next, for each point in your data set, compute any unobserved variables. Then, learn a classifier in the standard way by minimizing some loss function, but crucially, this classifier is only going to use any unobserved variables and any features that aren't descendants of A. The final classifier is guaranteed to be counterfactually fair. So let's see how this works in practice. We actually took a data set of 21,000 students from US law schools. And what we did first off is just see what happens when we just use all of our features to predict law school success. This is the sort of test accuracy that we get, the test RMSE. So this is a very unfair classifier, sort of the best accuracy you can hope for, though. Now, another unfair classifier, which we discussed earlier, is the one that just ignores the sensitive variables. And this is the sort of accuracy we get. But we want to be counterfactually fair. So here's a model we design specifically for this data set. It's a non-deterministic model. And when we fit this model and then just use U to make our prediction, we get a different accuracy. What you can think of this as, it's sort of the cost of fairness. We may think that the other model that I just showed might not be the best model, so we may use a slightly different model. This is a deterministic model. And you'll notice it uses slightly less strict assumptions. And so if we, again, we compute a counterfactually fair predictor, we get this sort of accuracy. So there's an interesting sort of trade-off between how strict your assumptions are when you make your causal model and the accuracy of your fair predictor. We also wanted to see if we take one of those models that I showed you and then we sample real data and counterfactual data and use the 2 unfair classifiers that I first mentioned to classify these 2 types of data, how different are those classifications? And it turns out on certain changes, certain counterfactual changes, these classifications are vastly different. And so we really need a counterfactually fair predictor. What I'd like you to take away from this talk is that race, gender, sexual orientation, and other things can cause machine learning systems to change unfairly. Our idea was to model how these attributes cause these unfair things to happen using causal models. We introduced a notion called counterfactual fairness that says a prediction is fair if it would give you the same prediction in a world where you had been different. And using this causal model, we have a mechanism to construct counterfactually fair predictors. A very simple procedure. This allowed us to make fair guesses of law school success. Now I'd like to invite you to come to our poster 187 because I think there's another exciting example that we've run this algorithm on for New York City stop and frisk data. I'd like to thank my co-authors, Chris and Josh, both of whom are here at NIPS, and they're co-first authors on this work, and also Ricardo Silva, who couldn't be here, but for a very good reason, because he just became a father a few weeks ago. And I'd like to thank you all for listening, and I'll take your questions now.
We have a few minutes for questions.
Thanks for the interesting talk. I have probably a very naive question, but so suppose you're looking at, for instance, gender, or let's take race. You're looking at race, and in your data set, you also maybe have the address of the person.
Yep.
Now, the address of the person will be, in many countries, correlated with the race. Won't this break your analysis? Am I wrong in thinking this breaks your analysis because you'd have creeping of information between those two?
So if you suspect that race is influencing address, what you'd want to do in your causal model is you'd want to say that race is a cause of address in that way. And then you could imagine there may be other variables that still aren't that you could still use, but that would sort of pollute address.
Okay, so what you're telling me is basically your analysis is conditional on having the causal model right.
Right. So you want your model to be as accurate as possible. That's right.
Thank you.
Yeah.
Great talk, Matt.
Thanks.
So it's a follow-up actually on the question that was just asked. And can you elaborate a little bit more on sort of when you can actually draw conclusions from this approach? So specifically, there are two ways in which things could break. One, there are other variables to consider that you didn't draw in your DAG at all. Mm-hmm. And the second is you actually did draw all the variables potentially, but maybe the wiring diagram is wrong.
Yep.
Right? Yep. And one thing that's interesting is in your example, for instance, clearly race and gender and these variables matter, but more likely there are all sorts of other variables matter, the pathways that matter we didn't even consider.
Yep.
And so do I really need to have the full diagram to ever be able to use this approach? And if so, does this mean it's unrealistic?
Right. Okay. So, how sensitive is sort of the fairness in the method? So, if you don't have all the information, yeah. So, so what you might want to do to sort of capture sort of other influences that you don't have in your data set is you might postulate other sort of latent variables. But in general, if you really suspect there isn't, the nice thing about having a causal model is it sort of allows you to make sort of conclusions about what other data you should have. But we didn't run actually sort of a robustness sort of analysis in that respect.
So if you go back to your experiments, for instance, and you know your diagram, that was super easy to follow. The question is, in reality, I'm sure there are tons of other things that matter.
For sure.
Right? So it might be worth thinking about the case that do you really need to observe all of those other things or have them in your wiring diagram?
Yeah.
Because invariably you're missing them.
No,
Maybe the point is what you could say is something not entirely about the exact causal effect being estimated being correct, but maybe you can bound it away from zero.
Yeah.
So some kind of bound that might be one way to proceed, because
right.
Invariably that diagram is going to be way too simple, right, to capture the kinds of structure that exists.
Right. So ideally as accurate as your model can be, but I think sort of I think this is really interesting sort of to look at how the causal effect might change without certain variables and how that affects fairness. But I think what we really wanted to emphasize in this work was that we should just start using these models, because if we just sort of use observational models, we actually have this interesting example in our paper where if you have this sort of fair causal model that produces your data, and if you don't actually take into account the causal relationships and you try to account for fairness using one of the techniques I mentioned, you can actually make it more unfair. So there are these weird unintended consequences, but without trying to model things causally. And so we just wanted to sort of say here are these two very, very nice communities, fairness, causality, and they should be looking at each other.
Hi. There are recent works using adversarial training, so to map the input X to some representation from which you should be able to predict the label, but not the sensitive attributes like race or gender.
Yeah.
So how's your model comparing to these methods?
Right. So there are certain cases of our algorithm that sort of look like those methods. So for example, there's our method is a generalization of a technique where you try to look at the influence of race on your features by just using a predictive model to take race and predict your features. Once you do that, you can subtract off your features, get the residuals, and that's sort of like making those features independent of your original sense of variables by computing the residuals. And so that, in that sense, that method sounds a bit like what you're talking about, but our method is a bit more general because you can consider sort of non-deterministic relationships and other sort of odd couplings, like maybe not linear models, but maybe interaction terms, more complicated things.
Great. Let's thank Matt.
Oh, thanks.
Okay, now we have a series of 11 spotlight talks.
Hi, I'm James McInerney from Spotify. My paper is about using ideas from empirical Bayes for doing hyperparameter tuning. Models and the methods for fitting them typically have parameters, which I collectively call theta. They also have hyperparameters usually, which I'm going to call eta, like the number of layers in a neural network, the number of clusters in clustering, number of topics in LDA. You get the idea. So here are some common ways for fitting hyperparameters. You could use expert knowledge, call up Jan LeCun, and take advantage of experience in general. But experience is hard to come by, so you might be more exhaustive and use something like a grid search or random sampling over the hyperparameter space. So they work pretty well, but they're less effective in higher dimensions, and they often shoot into the dark by evaluating hyperparameters that you already know are going to be bad. So a promising alternative is to build a performance model, what I call a performance model. It tracks the success of previous hyperparameters to choose where to evaluate next. This is what Bayesian optimization does. I'll call it Bayes-opt for short. More about that in a sec. So for now, just to be clear, all these methods split the data up into three subsets. There's the training data, there's validation data, and test data. In all the above methods, validation is used to select optimal hyperparameters, training is used to fit parameters, and only then does the test data yield the results of your latest publication, or you might also choose to just deploy the model. Now, as I said, Bayes-opt maintains a performance model, which you can think of as a meta model, that describes how well the original model performs as a function of eta. And eta is easier to say than hyperparameters, so I'll say eta. So the y-axis is performance on validation data, and the x-axis is configurations of hyperparameters. And the red line indicates the mean function of a Gaussian process, typically used for its convenient properties and because it will quantify uncertainty, letting us do things like exploration, exploitation, like balancing the two. So each time I evaluate an eta, I update the performance model, and each time I update the performance model, I choose the next eta to try. So this is all fine and reasonable, but the main thing I want to point out is that Bayes-opt contradicts itself in the following way. On the one hand, it assumes that it's expensive to learn parameters, or more generally to come up with a posterior over parameters. And it does this for every eta considered. Now, on the other hand, it picks the posterior corresponding to the best eta and throws away all the intermediate posteriors. It would be like going to the poster session tonight, visiting 100 posters, and forgetting 99 of the 100 because they were not as good as the best poster you saw. So in other words, surely the posteriors have something to say about the data, even if they don't come from the optimal eta. And the other danger I want to point out is that you could be overfitting validation data. So this is a robustness argument. And this danger grows with the dimensionality of eta. So what can be done? I think one promising avenue is to take inspiration from empirical Bayes. The idea is to use hyperparameter averaging using the performance model. So introducing a hyperprior, we seek the best hyperparameter while averaging out the etas. This is the familiar strategy of marginalizing out nuisance variables that we don't care about, and it turns out that this is pretty robust to overfitting validation data. In fact, if we could truly marginalize out eta instead of optimizing it, we could perform hyperparameter averaging, hyperparameter tuning or averaging without a separate validation data set, simplifying the pipeline used to compute, to compare and deploy models. So how is this done in practice? I'll give you an overall sketch. The idea is to use Monte Carlo averaging of models using samples of eta to form a predicted density on future data. What is unusual about this procedure is that it uses the data 3 times. Once to choose hyperparameters, once to choose hyperparameters, and a third time to choose parameters. Now, why is this not a terrible idea? Well, it turns out that using the performance model in this way is a kind of Thompson sampling, which is well known to work very well in reinforcement learning settings, where the reward is the log likelihood of the original model and the action is eta. Another argument is along efficiency lines. The number of eta evaluations is necessarily low, so let's squeeze everything we can out of the data while we can. Thanks at the end of my spotlight. I'm going to be at poster 44. Thanks.
Hi, everyone. I'm excited to tell you about a method we developed for producing approximate Bayesian posteriors for generalized linear models that can scale up to tens of millions of observations with tens of thousands of covariates. So we like using Bayesian inference because it provides us with a coherent measure of uncertainty, lets us incorporate prior knowledge, and do inference in complex generative models. As a quick review, our posterior is just proportional to the data likelihood times prior. But for most models that we're interested in, we can't take expectations under the posterior exactly. So we need to use some kind of approximate inference method. In particular, we like a large-scale Bayesian inference method to have the following 3 properties. The first, naturally, is scalability. It should be able to operate on streaming or distributed data sets. The second is that we like finite time, finite data guarantees. That is, if we have our posterior approximation, we'd like to know that it's in some sense close to the exact posterior. And moreover, if we're given a larger and larger computational budget, we'd like to be able to make our approximation better and better. The problem is that most methods out there, they can satisfy maybe 2 out of 3 of these, and it's hard to get all 3 at once. So that's what motivated our current approach. So before I tell you about that approach, I want to consider a particularly good or maybe even a best case scenario, and that would be exponential family inference. So if we're working with an exponential family, we get to decompose the dependence between our parameter and our data. What does this mean? Well, we can just take the sum, calculate our sufficient statistics, and then never look at the data again. We have this fixed dimension parameter that we can now use to evaluate our log likelihood in time independent of the amount of data we have. So that's great. What does this mean? Well, if we were to run MCMC, say, for t iterations, naively this would take order n times t time. So that's pretty terrible if n is really, really large. But if we use this exponential family structure, now it only requires n plus t time. Way better. Of course, most Bayesian models that we have are not exponential family, and so that's why we turn to something we developed called polynomial approximate sufficient statistics. The way we construct them is for each data, we calculate the monomials of that data point, of the components of that data point, up to some degree k. So we repeat this for each data point, and then we sum each of the monomial types, and this is going to give us our approximate sufficient statistics. And with a careful choice of reparameterization, eta, of our parameters, we're able to form an exponential family model that is very close to the original model. And now we can evaluate that in time independent of the amount of data we have. So this is great. Now we have something that actually satisfies all of our criteria. It's trivially streaming and parallelizable. There's minimal communication cost. You can use simple map-reduce type methods to calculate these approximate sufficient statistics. In the paper, we prove that this approximate posterior will be close in terms of Wasserstein distance, which means we get guarantees on the accuracy of our mean and uncertainty estimates. And finally, we can always just improve this approximation by considering higher order polynomial terms. Here's a taste of the experiments in the paper. We ran this on a Criteo advertising dataset that's publicly available. So it's just binary classification. So we used logistic regression. We got almost linear speedup as we increased the number of cores. And this translated to being able to process 6 million observations with 1,000 covariates in just 16 seconds when we were using 22 cores. And we also have streaming experiments where we went up to the tens of millions of data points. And just as a reminder, this is giving us a full posterior approximation. Typically on a problem of this scale, people would use something like an online stochastic gradient descent algorithm and just get a point estimate. So if you'd like to learn more about the method and the experiments, come to our poster 191 tonight.
Hello, everyone. I'm Yi from the University of Chicago. I'm going to talk about multi-resolution kernel approximation for Gaussian process regression. This is joint work with Rishi Konder and Jonathan S. Grace Winkler. Gaussian processes have been one of the standard methods of Bayesian non-parametric inference in machine learning. Unfortunately, Gaussian process regression generally does not scale to beyond a few thousand data points, which makes the exact inference difficult. Therefore, kernel approximation methods are used instead. When concerned with the general Gaussian process regression problem, it is assumed that the Gaussian process observed as some coordinates. The vector of the values are just one sample from a multivariate Gaussian distribution with a dimension equal to the number of the observed coordinates. From the plots, the left are draws from the prior function distribution, the middle are draws from the posterior, and the right are mean prediction with one standard deviation shaded. In Gaussian process regression, the posterior mean estimate can be written as this formula. From this formula, the inference reduces to just having to compute the inverse of an augmented kernel matrix K'. So the problem here is how to approximate K' to make inverting it easier. The most commonly used methods are called the global low-rank methods, which are known as the nice-strong approximation. The idea is to take a smaller set of landmark points to approximate the kernel function in terms of the similarity of data points to each of the landmarks. The limitations of the global low-rank methods are, first, it is inherently low-rank. Second, from the formula, the inverting kernel matrix indicates that the low eigenvalue eigenvectors should dominate. However, multiplying the cross-covariance kx cancels this effect. So it is really not the kernel matrix itself, but the relationship between the kx and the inverting kernel matrix determines the inference results. In this work, we present a data-adapted multi-scale kernel matrix approximation method called Multiresolution Kernel Approximation, or MKA in short, which reflects the insight that distant clusters only interact in a low-rank fashion, but is more flexible than existing hierarchical matrix decompositions. We define the core-diagonal property of a symmetric matrix. Instead of assuming the kernel matrix is low-rank, the core-diagonal compression of matrix captures the structural property of a kernel matrix in different resolutions. MK is a meta-algorithm in conjunction with different core-diagonal compressors like the sparse PCA and the multi-resolution matrix factorization. Compared to sparse PCA, MMF has computational strength and stronger bounds on sparsity. Specifically, MMF yields a factorization of the form of a factorization with a form with a series of sparse orthogonal matrices and a core-diagonal matrix, which makes inverting very easier. In simplest case, the Q here are just given rotations. We apply MKA to Gaussian process regression problem. In particular, we compute the MKA of the joint trend test kernel matrix and use the Sherman-Morrison-Woodbury formula to recover the approximation of the inverting training kernel matrix. Now let's look at the qualitative behavior of different approximation methods on a 1D toy data example. From it is obvious that the MKA can fit the data almost as well as the exact inference with full matrix does. In addition to this, we also apply our method on large-scale data set to get very good results, which indicates that our method is a promising approach for large-scale kernel matrix compression. In conclusion, we believe that whether a learning problem is low rank or not depends on the nature of the data rather than just the spectral properties of kernel matrix. And more importantly, we propose MKA, which allows fast direct calculations of the inverse of a kernel matrix and its determinant, which are most always the computational bottlenecks in Gaussian process problems. Thanks for your attention. To see more results on real data, please remember to visit our poster tonight.
Welcome to my talk. My name is Matthias Polocek, and I'm from the University of Arizona. I'm presenting joint work with Jelai Wang from IBM and Peter Fraser from Cornell. The title of the talk is Multi-Information Source Optimization. Let me begin by explaining what a MISO problem is. Our goal is to optimize a complex design X, specified by D parameters, usually at most 20, at an expensive to evaluate black box function G. So expensive to evaluate means that each function evaluation takes several minutes, hours, or for instance in case of biochemistry, even weeks. Black box function means that when we query g of x, we just get the function value, but no derivative information. So now we want to find a global optimum of such a multimodal function. To our help, we have some information sources that approximate g of x, but they vary in their quality and vary in their cost. So now MISO has lots of very exciting applications. I'd like to give you a few examples. For instance, consider your favorite ride-sharing company. Then they want to study the effect of certain market parameters, and they can either evaluate them in the real world, which also means in real time, in a city, hopefully far away, or they could use a discrete event simulation, which is much faster. Similarly, they want to optimize the hyperparameters of a machine learning algorithm. I can either train on the whole data set, or could use a small subset, or maybe a small related data set to speed up the optimization process. A very cool application is the design of aerodynamic structures. You can either build a prototype and evaluate this prototype in a wind tunnel, or could use a CFD simulation. And this CFD simulation, of course, is much cheaper and also much faster. So where's the catch in using information sources? The problem is information sources are subject to two kinds of uncertainty. The first, what we call model discrepancy. Model discrepancy originates from the fact that the internal model of an information source may be inaccurate, may be biased. In this example you see here, the CFD simulation does a pretty good job, but there's an area where the observed performance deviates from the model value. And this difference of the internal model value minus the true performance, that's what we call model discrepancy. The second type of uncertainty occurs when we observe the internal model value. This is just observational noise. In our paper proposed a MISO-KG algorithm that can solve such problems. It's based on two components. The first is what we call our MISO-specific generative model that is able to handle both types of uncertainty, the model discrepancy on the one hand and the observational noise on the other hand. Particularly, it's able to learn the relationship of data from data, relationship of information sources from data. Particularly learns the covariance structure. The second component is the value information analysis, which decides where to sample and which information source to query. And this information analysis balances off the expected information gain and the cost of each query. In our paper, we give an efficient parallelization of this computation, and we also demonstrate in experiments that MySQL makes better decisions what information source to query and which design to query for. There's also implementation of our algorithm online, so feel free to check it out. In our paper, we also give a theoretical foundation for the MySQL algorithm. So we show that short term, for one decision, MySQL algorithm is optimal in the sense that it maximizes expected information gain per cost for each query. But also long term, we can show that our algorithm is guaranteed to be near optimal. Our proof technique is short and quite elegant, so it might be of independent interest for other algorithms as well. And we show that MySQL algorithm is consistent for discrete domains, which generalizes in the result by Frazier-Powell dianique to the MISO setting. Many thanks.
Hi, I'm Hugh. I'm here to talk about doubly stochastic variational inference for deep Gaussian processes. This is work with my supervisor, Mike Deisenroth. So as we've heard, GPs are priors over functions. On the left, you can see a covariance matrix, which is plotted as a heat map, and in the middle are 5 samples from a zero-mean Gaussian with that covariance matrix. So this can work very well. We can do inference exactly in some situations, and for this example, we get really nice fit and good error bars. But it's not always this good. So if the covariance is misspecified, as in this example, it's actually a very bad model. So here the data has some non-stationary aspects, and that is not modeled well by this Gaussian process. Now we can remedy this situation by just changing the prior. So here is an example, prior covariance, which looks more suitable. It has some non-stationary effects like the data, and unsurprisingly then, the posterior is a really good fit. But suppose someone mischievously inverted the data like this, then now it's no good again. In fact, it's even worse than before. So the prior is misspecified, and the predictions are very bad. We can fix it again by just flipping the prior, but the interesting question is, what if we don't know which covariance to use in advance? If we had, for example, these two, and we believed with equal likelihood it was one of these two, we can't express this as a single layer GP. And by the way, I should point out that we're not interested in choosing what the prior is after seeing the data, for example, by maximizing marginal likelihood or something. We want to be fully Bayesian. So lots of ways we can solve this problem, but we're going to be non-parametric about our uncertainty of the covariance and use another Gaussian process. So here's one way we can build this with the deep to make a deep GP. So here I've got a sample from that covariance, and I'm going to use the output, so the y values of that sample, to generate a new covariance, and it looks like this. The reason it has loops in it is because this function that I sampled was non-injective, so there were several inputs for the same output. I can draw a sample from that covariance, and it looks like this. And notice it has some funny non-local symmetries in it. And if I use that to generate yet another covariance, I get this rather interesting looking pattern. But unfortunately, the sample you get at the end is not particularly, well, it's a slightly strange function. Turns out this model is degenerate, and it collapses as the number of layers increases, as shown by this paper in 2014. So this is a bit of a problem. We propose to fix this with a linear mean function. So in the previous slide, everything was zero mean, whereas here we're going to use the identity mean function. If we construct a covariance from that solid curve, then we get something like this, and we can keep doing this for multiple layers, and we end up with something that is more complex than a single layer GP, but without the pathologies of the single layer model. Here are some more samples. Just to check, with this prior, we really can model these two types of data sets using exactly the same prior with no high parameter optimization whatsoever. So inference, we propose a new variational posterior, which itself is a deep GP. Our bound admits nice unbiased samples, which we can take very easily. On the left is the model, and there is our variational posterior. The mean and covariance functions, you can come to our poster to see the details, but also Mark van der Wilk has he's presented the same functions as in his talk earlier this afternoon. In previous work, they did not have the connection between the layers, as you can see on the right-hand side, and also did not have the mean function. results. We do a range of experiments on regression, classification, multi-class classification. I'll highlight here one particular data set where we use 1 billion data points, so we can certainly scale to very large data, and we see that the deeper models far outperform the shallow, the single layer model. We also see that you can come to Poster to check out the results, that we don't observe overfitting even on very, very small data sets. A consequence of our linear mean function is that it's very easy to initialize, and so it works out of the box. We can just set all the variational parameters to 0 at the beginning, and that seems to work pretty well. The code is, you can see at the link, and uses GPFlow. In summary, we solve the problems of degeneracy and initialization with the mean function. Our inference method is extremely scalable, and it maintains a richly correlated posterior, which itself is a deep GP. And we don't observe overfitting, even with lots of layers. Can't post there if you want more details. Thank you.
Hi everyone. In this talk, I'm going to present my most recent project in causal inference called permutation-based causal inference algorithms with interventions. Before introducing the algorithm in detail, I start with introducing the motivating example. Currently, technology in system biology has enabled us to obtain large-scale gene expression data under different cellular contexts. In addition to this, a new technology called Probabilistic has also allowed us to obtain large-scale gene expression and interventional gene expression data, namely the kind of gene expression data after doing the gene knockout experiment. With the availability of both observational and interventional data, it is now an open question that how we could make use of this kind of data to learn the underlying gene regulatory networks. In particular, since the underlying network is a gene network is a direct network, we could this is actually a causal inference program. Basically, there was one method available that could make use of observational and interventional data called GIES method. It is a discrete optimization method that greatly searches within the space of directed circuit graph, or DEX in short, by optimizing the BRC scoring function. The following figure shows an example of the space of DEX. Here, the two DEX are neighbors with each other in this space if they differ by one edge. However, it has two limitations. First, it is a parametric approach that relies on the Gaussian entity of the data. So, in other words, since the BRC scoring function is a likelihood-based scoring function. In addition to this, it is still an open question that whether GIES is consistent or not. Or in other words, whether it is guaranteed to output the true causal model as the number of data goes to infinity. Our contribution in this project is mainly threefold. First, we have proven actually GIES is not consistent. Or in other words, we have proven actually even with infinite amount of data, GIES is not guaranteed to output the true causal model. In addition to this, we also developed a new algorithm that could make use of observational and interventional data called the interventional gradient sparsity permutation algorithm. It has the advantage that it is a non-parametric approach. In addition to this, it is also the first algorithm that has been guaranteed to find the true causal model by using observational or interventional data. We also evaluated the performance of our algorithm on real-world datasets, including protein mass spectrometry data and probabilistic data. Next, we introduce the main innovations of our algorithm. First, we associate a DAG with a permutation and an undirected graph. In this case, secondly, we perform gradient search within the space of permutations, which is a much smaller space as compared to the space of DAGs. The following figure shows an example about the space of permutations. As we can see that the space of permutation is a polytope-like space, and our algorithm could be interpreted as a simplex type algorithm that greatly searches within the edges of the polytope to minimize the number of edges for the associated DEX. Since the real-world dataset is usually non-Gaussian, By nature, non-parametric approaches usually has wider applications as compared to the parametric approaches, such as GIS method. One example is the zero inflation problems in single-cell RNA-seq data. Our real-world analysis also shows that our algorithm has better performance compared to GIS on these kind of data sets. For more information, please go to our poster. Thank you very much.
Hello, everyone. I'm John Holleran, a postdoc at UC Davis, and today I'll be talking about gradients of generative models for improved discriminative analysis of tandem mass spectra. Tandem mass spectrometry is the most widely used technology to identify the proteins of a biological complex sample, such as a drop of blood. A typical experiment is as follows. We begin with our complex sample, which is comprised of proteins. We then run 2 rounds of mass spectrometry on it to obtain a collection of spectra. Now, each spectrum in our collection is representative of a protein subsequence called a peptide. We then identify each one of these spectra using a scoring algorithm to obtain a list of peptide spectrum matches, or PSMs. Now, in practice, PSMs are poorly calibrated, which makes it difficult to compare one PSM to another. This necessarily leads to diminished search identification accuracy. To fix this problem, PSMs require post-processing and recalibration, which typically involves using an SVM. The resulting recalibrated PSMs substantially improve spectrum identification. In previous work, generative models were used to improve discriminative recalibration as follows. PSMs were fed into a dynamic Bayesian network called DRIP. Max product inference was then run, and the resulting Viterbi path was parsed to derive a set of heuristic features. These heuristic features improved SVM recalibration by a drastic amount, resulting in over 6% average improvement on overall datasets. In our work, we show that a non-heuristic approach works a lot better. Specifically, we derive the gradients of DRIP. Using these gradients, we curate the feature space. The resulting Fisher kernel results in state-of-the-art accuracy of an average of 12% over all datasets. Now, in order to extend the Fisher kernel framework to other scoring functions, we designed a DBN called Thesus. Thesus is a general PSM decoder which models a very large class of scoring functions. Now, using Thesus, we demonstrated that the Fisher kernel improvements actually extend to some of the most popular scoring functions widely used in practice. Furthermore, Thesus also allowed completely unsupervised learning through a mixture of gradient descent and max product inference. For more information on this topic, please visit me at my poster, number 93. Thank you.
Hi, I'm Tianxiao Shen. I'll talk about style transfer from non-parallel text by cross-alignment. This is joint work with Tao Lei, Regina Barzilai, and Tommy Yakola. Language is rich and powerful. We can express the same meaning in many different ways. It can be brief or verbose, colloquial or professional, polite or impolite, and people have their different personal styles. Can we train machines to perform this task? Given a sentence, rewrite it into another style, say Shakespeare style or Trump style. Instead of using massive amounts of parallel data like in machine translation, we are interested in a more realistic scenario where we only assume access to 2 non-parallel corpora and learn to transfer the style between them. This is an important step towards real language understanding, and it has wide applications, such as to design personalized chatbots and to appropriately convey a message according to different social contexts. Non-parallel style transfer has been extensively studied in computer vision. Given a photograph, transfer it into some artistic style like Monet or Van Gogh. For language style transfer, however, we have different challenges. The first challenge is conceptual. Language style is more subtle than image texture, and we want to ensure content preservation, that the transfer sentence should be semantically equivalent to the source sentence. Another challenge is technical. A natural language sentence is a sequence of discrete tokens. Direct transfer on the surface space is not a continuously optimizable process. To address these challenges, we propose to learn a mapping between sentences and continuous latent representations, and further decompose the latent representation into style and content components. Then we modify the latent style representation to realize style transfer. Specifically, we assume that two corpora x1, x2 have a shared latent content distribution pz, but rendered in different styles y1, y2. We learn an encoder E that removes the style information and encodes a sentence X into its content representation Z. Meanwhile, we learn a generator G that generates a sentence X from a given style Y and content Z. E and G form an autoencoder when applying to the same style, and form a transfer model when applying to different styles. The transferred sentences from one style should match example sentences from the other style as a population. To deal with this discrete comparison, we introduce a refined alignment of sentence representations across text corpora. The hidden state sequence of reconstructing X1 by teacher forcing and transferring X2 by soft self-feed are passed to a discriminator to be aligned. Our cross-aligned autoencoder is the first discrete transfer model that learns from non-parallel data. Our model can be used to transfer the sentiment between positive and negative reviews. For example, it transfers "do not like it at all" to "all in all, it's great." Transfers "the sandwich was very greasy and soggy" to "the sandwich was very tasty." And transfers "mediocre dim sum" if you are from Southern California to "good dim sum" if you have Korean friends. It achieves 78.4 sentiment accuracy as measured by a sentiment classifier. According to human evaluation, it successfully rewrites 41.4% of the sentences to the opposite sentiment while preserving the content. Decipherment is another scenario that calls for non-parallel style transfer. We focus on the decipherment of word substitution ciphers, and our model achieves BLUE score 57.4 by evaluating on parallel sentences. Finally, we tried our model to transfer between different poetry forms, Chinese 5-character poetry and 7-character poetry. Our code and dataset are available online. If you want to know more, please come to our poster number 94 tonight. Thank you.
Hello everyone, I'm Minzhe Wang. Today I'm going to present our paper, Permutation Selection for Theorem Proving by Deep Graph Embedding. This is joint work with Yi Hechang, Jian Wang, and Jia Deng from University of Michigan. In this work, we address the problem of automated theorem proving. For example, suppose we have conjecture California is the largest state in US by area. We can express this conjecture as a formal statement. For x, if x is a state and x is the US, then the area of x is smaller than the area of California. Given a knowledge base of existing facts, the task of theorem proving is to generate a proof or disproof of the conjecture. Automated theorem proving is useful for many applications. For example, it can be used to prove mathematical theorems, to formally certify computer programs, and to answer questions in general. In this project, we focus on case subtask of theorem proving called permutation selection. The goal is to select facts relevant for proving a given conjecture. We formulate permutation selection as a binary classification task. Given a conjecture and effect, we predict whether this effect is relevant to prove the conjecture. For example, after applying permanent selection, we can discard the irrelevant effect and send only the relevant ones to a theorem prover. Permanent selection is important because theorem proving is essentially a search problem, with the goal of finding a sequence of deductions leading from its presumed fact to the given conjecture. But with a huge number of facts in a knowledge base, the search space can explode quickly. With permanent selection, we can hopefully reduce an encyclopedia to a single-page cheat sheet, such that the theorem prover's life becomes much easier. In this work, we take a machine learning approach where we seek to learn useful heuristics for permanent selection. We convert both the input, conjecture, and fact into vectors and send them into a binary classifier. The key remaining question is now how to embed logical formulas into vectors. We observe that a good vector embedding of logical formulas should be invariant to variable naming. That is, if we replace variable x, y with s and t, the meaning of formulas stay the same, and the vector embedding should stay same as well. We propose a method to achieve such invariance based on the idea of graph embedding. Given a formula, we start from its parse tree, merge the leaf node that represents the same variables, and connect each quantifier with its variable. Also, we drop the original variable names and replace them with a generic name var. This graph representation is invariant to variable naming because the original variable names has been removed. At the same time, there is no loss of semantics because we still know which quantifier bounds which argument of which predicate. Also, a side benefit is that the graph makes the syntactic structure explicit. Given the graph, we now embed it into a vector. We assign each node an initial embedding based on its token, and we use a small neural network to update the embedding of each node based on its neighbors. We iterate multiple times to encode bigger graph structures. At the end, we maxpol all node embeddings to obtain a single embedding for the full graph. An important detail is that our embedding are sensitive to the ordering of function arguments. For example, in our method, f of a and b and f of b and a can have different embeddings. Please refer to our paper and poster for more details. As a recap, we use graph embedding to convert formulas into vectors, followed by a binary classifier. The whole system can be trained end-to-end. We evaluate our approach on the ultra-stable dataset, which is a recently introduced theorem proving benchmark that contains more than 2 million conjecture fact pairs expressed in higher-order logic. Our approach achieves the new state of art on this benchmark, outperforming previous approaches, which are based on sequence embedding. To summarize, in this work, we address the problem of permanent selection. The key idea is to represent the formula as a graph and embed the graph into a vector. For more details, please read our poster tonight. Thank you for your attention.
So hello everyone, I am Ahmed from UCLA, and I'll be discussing briefly our work on developing probabilistic models for survival prediction in the presence of competing risks. And this is joint work with my advisor, Professor Mihaela van der Schaar. So the most common form of survival analysis problems is that we are trying to model time to event data with respect to a single endpoint. So for instance, if we want to model the survival behavior of cancer patients, our only endpoint would be the death of patients due to cancer. But a more general form of a survival analysis problem would include n competing events or n mutually exclusive endpoints. So in the same context of modeling the survival behavior of cancer patients, these endpoints could be death due to cancer or death due to cardiovascular disease or death due to any other cause. So the objective of such type of analysis is to learn on the basis of time to event data a joint risk profile that describes through a cumulative incidence function the risk of an individual patient with respect to multiple clinical endpoints over time and how these risks are evolving over time. And that's really useful for clinicians who are trying to optimize long-term treatment plans for patients who are having comorbidities or having high risk for multiple types of diseases. So our objective is to model time to event data that exhibits competing risks. And that's the data structure that we are dealing with. We have patients with features, and for every patient we have survival times and the event that happened to the patient. So in this figure we have two types of events colored in red and blue. And the predominant method that's being used by clinicians and biostatisticians in clinical research is the Cox proportional hazard model. So that's really a nice model that's interpretable because the coefficients of the model tells you the contribution of individual features on the survival behavior, but it's essentially a linear model that cannot capture any complex nonlinear interactions on the data. So the model that we developed is an accelerated failure time model, and by that I mean that we explicitly place a distribution, a joint distribution for the survival times of the patients as a function of their features. And the way we link the patient features to the survival time distribution is through a deep Gaussian process. So the input to the model is the patient's features, and then we have a sequence of layers that will learn a data-driven representation for the patient's features, and then the output of the last layer of the Gaussian process is multidimensional. So we have a random variable representing the survival time for every competing risk. And then what we observe in the actual data is the minimum of all these outputs. So because the event that happens first is the only event that materializes and all other events are censored. So if we have k competing events and only one event would happen and censor the others, the random variables that correspond to the k-1 remaining events would be latent variables that we want to account for in our inference algorithm. So we know that there is a variation lower bound for the likelihood of the observations for the deep Gaussian process. So we proposed an approximate inference algorithm in which we have a data augmentation scheme in which we impute the unobserved censored survival times using the current guess of the model, and then use these and feed these into the variational objective and re-update the model, and then go through this process iteratively. So in the cases in which there are nonlinear interactions between the patient covariates and the relationships to the survival times, we can show that in terms of concordance metrics, our model can perform the conventionally used linear models like Cox models or fine-grained model. Thank you.
Hi, everyone. I'm Emily Denton from New York University, and this is joint work with Vinesh Barodkar. I'm going to be telling you about a model for learning disentangled representations from video. So DRNet, or Disentangled Representation Net, is a disentangling autoencoder that factorizes image sequences into temporally constant and temporally varying components, which we call content and pose, respectively. So the motivation for this work comes from the fact that in many video sequences, there's a large portion of the scene that remains constant across time, whereas other aspects of the scene are going to vary in regular ways. So our method utilizes this naturally occurring video structure as a supervisory signal. So DRNet is based on an encoder-decoder architecture. There's two separate encoders, each of which see a different frame in the video sequence. A content encoder extracts time invariant information, which in this sort of toy video sequence corresponds to lighting, object identity, and camera viewpoint. A pose encoder will extract time varying information, such as the object's orientation. A frame decoder will take as input a content vector from a frame at time t and a pose vector from a frame at time t plus k, and decode the frame at time t plus k. So since the target for the frame decoder is the same as the frame that's seen by the pose encoder, we need some additional constraint on the representation in order to stop the pose encoder from representing everything about the image, in which case we would just have a standard autoencoder. So we prevent the pose encoder from carrying all of the information by adding an adversarial loss on the pose feature space. So this loss forces as much information as possible into the content representation, in particular, everything that's predictable about the future frame from the past. So the adversarial loss is defined by a fully connected neural network, which we call the scene discriminator, that's going to take as input a pair of pose vectors. So the pair of pose vectors is either extracted from the same video clip or a different video clip, and the scene discriminator is trained to differentiate between these two conditions with a binary cross-entropy loss. When the scene discriminator is being trained, the gradients don't flow to the pose encoder, it's held fixed, just as in a standard sort of GAN training framework. The pose encoder is trained adversarially to maximize the uncertainty of the discriminator's output on pairs of frames from the same video clip. So this adversarial loss intuitively is discouraging the pose encoder from carrying any information about aspects of the video sequence that are constant across time. So putting this all together, we have a content encoder, a pose encoder, and a frame decoder. And the model's trained with a weighted sum of 3 different loss terms: a reconstruction loss, a similarity loss that encourages temporally nearby content vectors to have similar representations, and an adversarial loss. So what can we do with this model? At test time, we can perform an analogy task where we take the content representation from one image and the pose representation from another image and synthesize a new image. So this type of combination was never seen during training, and so the ability of the model to sort of synthesize new images like this indicates that the model really has factorized content and pose. So here are just some examples of the model doing this. We take the content from the images along the leftmost column and the pose from images along the top row. So slightly more interesting is the idea that we can use a disentangled content and pose representation to do really easy video prediction. So a forward model in this case only has to consider how the pose vectors change because the content is going to remain fixed across time. So what we did is trained an LSTM to condition on some pose vectors and predict future pose vectors. And this prediction is all done in latent pose space rather than in pixel space. And then a frame decoder that we have is just used to map the content and pose vectors back to images. So we evaluate the video prediction capability of our model in the KTH data set. So this shows our model taking 10 frames as input and generating 30 frames. So the top row shows the conditioning frames and the ground truth future frames. The second row shows our generations, which we see remain fairly crisp and coherent. The third row shows a baseline where we trained an LSTM on an autoencoder's hidden representation rather than our factorized DRNet representation. And the bottom row shows a very strong video generation baseline called the motion content net. So our generations also remain fairly coherent up to 100 time steps in the future. We tend to not see the sort of image artifacts that appear in lots of other sort of video generation data sets. This shows, again, the top row, our model, the DRNet, and a very strong video generation baseline, the motion content net. And we sort of hypothesize that our images stay closer to our generations stay closer to the image manifold because our predictions are all done in this low-dimensional latent pose space, and so small prediction errors in image space don't get amplified when the generations are sort of recursively fed back into the model throughout generations. So thanks for listening. If you want to hear more about this, come visit our poster. It's number 153 tonight. Thanks.
That concludes our session. Let's thank the speakers once again.